This is the one before last colloquium that we had. This one is broken into two parts, as we usually do, and next week will be the last colloquium. It will be dedicated to the Ligo event, the two-neutron star merger, given by Ido Berger next week. The other special thing about next week is that after the colloquium, we'll have a party, a winter party for the holidays. So that will be at 3 p.m., right, Bill?
Yep.
And Bill was instructed to find the best cake in town. It will be special, right?
We'll do our best, yeah.
Chocolate?
Sure, yeah, absolutely.
Any favorite color? I think, given it's black hole initiative,
sure.
We should have a dark chocolate.
Dark chocolate cake, yeah, sounds good.
And it will be festive, so Bill will arrange this conference room after the colloquium. The one other thing I wanted to mention is that yesterday I got an email from a reporter, Newsweek reporter, about a new paper that is about to come out in Science magazine about a black hole. I just wanted to mention it because it's significant in one respect. This black hole binary is called V404 Cygni. Ramesh probably recognizes it. You've written it. It's a 9 to 10 solar mass black hole in a 6.5 day binary orbit with a 0.7 solar mass companion. And what's special about this paper is that they measured a flare at many wavelengths, radio, infrared, optical, and so forth, and they were able to infer the magnetic field at the base of the jet, presumably, very precisely, 461 plus or minus 12 Gauss. So that the parameters that they infer are unprecedented in precision, and they would, in principle, allow theorists to perhaps model the conditions there. So this should come out in Science within a couple of days, and anyone that wants to read it, I have it.
Expected?
It's a bit lower.
Seems low.
It's low. So the comment that should be made is that this field is lower than expected, and as a result, the electron population that needs to produce the radiation has to have a higher Lorentz factor than previously thought.
Much lower by orders of magnitude, or?
Yeah, according to the paper.
You
I
think,
would wonder how they measured it.
you think tens of kilogauss or?
Depends what base of jet means, but if it's really at the black hole, I would say, yeah, it should have been at least 10 to the 6 to 10 to the 8 Gauss.
Right.
Yeah.
Yeah, that's
also now
consistent with
Lorentz
what they're saying
invariant.
here. So, Ramesh, perhaps you will have a look at this paper and let us know what you think.
I think the measurements are wrong.
It's ruled out by theory.
Yeah.
Okay, so I'm delighted to welcome Professor Jos Uffink to the Black Hole Initiative and to the Black Hole Initiative Colloquium series. Professor Uffink is a professor of philosophy at the University of Minnesota. He works generally on philosophical and historical aspects of physics, and more particularly on foundational philosophical and historical aspects of quantum mechanics and statistical physics. Yesterday, the second mini workshop on philosophy of extreme spacetimes, we had the benefit of hearing his insights in a wide-ranging, fascinating discussion on statistical issues in physics, in particular based on a paper that he's written recently with Giovanni Valente on Lanford's theorem and the limits of irreversibility. And I'm pleased to say that we're going to get the benefit of his insights again today as he tells us about black holes and thermodynamics.
Thank you very much for this nice introduction. When I got the invitation to speak here, I felt very flattered and decided to talk about a topic that might be of interest to you. And of course, I am aware that this is a bit dangerous to speak here at the lion's den of black hole specialists, where I cannot count myself as a specialist in black holes. But I want to talk about a subject that has been the topic of some controversy, or at least some difference in opinion, about the so-called black hole thermodynamics. And the question which opinions are divided are whether this is merely an interesting analogy between black holes and a theory of orthodox thermodynamics, or whether, on the other hand, it is something like an identity, that is to say, whether it really makes sense to regard black holes as thermal systems that have a temperature in the ordinary thermodynamical sense, and so on. So this is the question that I wanted to address today, and to be sure I will address it more from the thermodynamic side than from the black hole side. And I actually am not going to claim something about it. I'm just going to conclude that there are certain challenges in my mind that ought to be addressed in this discussion that I haven't found being discussed in the literature as I know it. So that is the question. I think it's already here on the last point. The first is just historical introduction. In particular, Eric Curiel has been arguing that black holes are really hot and that they're thermodynamical objects. So to start off, I want to...
Are you distinguishing between thermal systems and statistical systems?
I'm not talking about statistical systems. I'm talking about orthodox thermodynamics, not about statistical mechanics or statistical thermodynamics or any statistical theory.
Right, but thermodynamics is always an approximation, right?
Thermodynamics is just a particular theory. I'm not talking about its validity. And, well, let me try to continue here. I first wanted to say something about what it means for some theories or descriptions to be analogous, and when you decide that there is more than just an analogy. And I will not go into the philosophical literature on what analogy means, because there's simply too much of that. I will just try to indicate what I mean by comparing two sort of extreme examples. The first one is, which I think are actually really clear-cut cases. So the first one is the analogy between the electrostatic Coulomb law and Newton's law of gravity, which, as you can tell, are both inverse square force laws, and this is very analogous to each other, and in fact you can exploit that very much. You can apply potential theory to both force laws and describe them in terms of a potential that will satisfy the Laplace equation, and once you've got the form of the potential, then you can derive the force by just taking the gradient. That applies in both cases, so the analogy really goes through very far, but in this case nobody will argue that this means that the electrostatic force law is just gravity, because there are also, of course, plenty of disanalogies between the two. On the other hand, when Maxwell discovered that his electromagnetic equations admitted of waves that will propagate at a velocity which he could determine from the constants in his equations, and he found out that it was equal to that of the velocity of light, he immediately jumped to the conclusion not just that light is analogous to electromagnetic radiation, but rather that light is a form of electromagnetic So in this case, he immediately jumped to an identification of the two areas and didn't stop at the case at the claim that it was just an analogy. Of course, it's not really an identity, but only an identification. I changed the word here because you clearly cannot argue the other way around that all electromagnetic radiation is just light. So I hope these two examples make clear what is at stake, or do we merely want to say, oh, this thermodynamics and black holes are two different studies on different types of objects that have a sort of similar kind of behavior, or whether we want to say that black holes really are thermodynamical systems. Now, when it comes to thermodynamics, black holes are not the first type of generalization of first cases where people have tried to generalize thermodynamical concepts beyond the original intended meaning.
I have a comment about.
Yeah.
I'm not sure anybody ever really wanted to argue that black holes were thermodynamical systems. So people wanted to argue that Boltzmann, of course, and others argued that thermodynamic systems are really statistical systems.
Yes.
And that that's a better way of thinking about thermodynamic systems.
Yeah, but that's a different theory.
It's a different and more complete theory. It's a theory which reduces to thermodynamics in some approximation. So my understanding was that people wanted to argue that black holes were statistical systems. That they obey laws that look like, they undeniably obey laws which have a strong resemblance to standard thermodynamic laws, and that they could be governed from, they could be derived by statistical reasoning from statistical systems. Now this hasn't been proved, but it's an outstanding conjecture. So I don't quite know what it would mean to establish directly the statement that the black hole is a thermodynamic system, because clearly you have to enlarge your vision of what a thermodynamic system is to include black holes. But it is meaningful to say that the behavior of black holes can be derived from statistics and in more or less the same kind of reasoning that thermodynamics can be derived to.
I'm not denying anything you say, but
okay.
maybe clarify. When I talk about black holes, or when I talk about thermal systems, I'm talking about systems as they are characterized by a particular theory. And in the case of orthodox thermodynamics, that is not a statistical theory. When I talk about thermodynamics, I'm talking about a tradition that goes back to Clausius, Kelvin, Planck, and so on. At least that's where the theory started. It's not a statistical theory.
Right.
It may be that that theory is only an approximation for the real world, but there are many physical theories that are only approximations. That doesn't stop us from studying them.
Right.
Similarly, when you study black holes, you can do that also by choosing a particular theory. If you use general relativity, then that's not a statistical theory either, and the black hole as characterized by general relativity is therefore not a statistical object. Of course, you might say maybe that's only an approximation, and in the end we will need some type of statistical or quantum theory to describe these types of objects. Yeah, that's fine. I'm not going to discuss that. I'm actually asking whether relation between two types of theories is such that there is merely an analogy, or whether they support a stronger claim. Even if those theories are just approximations from the point of view of a deeper lying theory, or from the point of view of reality, that's possible. But that is a further question than the one that I am addressing. Does that make sense?
I'm just wondering why we should be concerned, whether it's true or not.
People are concerned. So I'm not.
People are concerned.
I can't tell you why they should, or why they are when they shouldn't have been. So, to come back, as I said, there have been other cases where people have tried to extend thermodynamical notions to other areas. And one of the most famous cases is that of information theory, when Shannon introduced a particular quantitative measure for information. He called it entropy, as you might well know, on the advice of John von Neumann, who said you should call it entropy because nobody knows what entropy means, and therefore if you use the term in a debate, you will always win.
Still true.
James has taken that notion and claimed about that notion even far more literally than Shannon himself was prepared to do. And he argued, at least in the case of statistical mechanics, that that is just a special case of information theory and statistical inference. So he wanted to reduce entropy to information rather than the other way around. More recently, there's been a lot of interest in trying to quantify a sort of degree of entanglement between composite quantum systems. And the type of measure that is usually chosen for that case is the von Neumann entropy. And there's been a lot of interest in trying to develop analogies with thermodynamics in this case too. Especially whether the entanglement theory is somehow irreversible in the same sense as thermodynamics is. Although in this case the idea is that whereas entropy cannot decrease in the course of time, entanglement cannot be diminished. Entanglement cannot be increased, whereas entropy can only be increased. In any case, when I think about those previous cases, I would argue that thermodynamics is not just a theory about entropy. There are a whole lot of other important notions in the theory, like heat, work, temperature, equilibration, and adiabatic processes. And although one might have an analogy for entropy, the analogy has to extend much further than that before I can take it seriously. So, to go to the information thermodynamics case, since nobody, to my knowledge, has ever told us what the analogy of temperature is in the case of information theory, I think it's just a half-baked analogy. In the case of entanglement, the situation is somewhat better off because there is an analogous notion to the concept of an adiabatic process in terms of the LOCC operations, where LOCC stands for local operations assisted by classical communication. So the idea is you might have a distributed quantum system and you can perform local operations on each of those subsystems, and you might classically communicate the results of your local measurements to other parties and do any type of sequence of operations that are permitted by this type of instructions. And the idea of the claim is that in no case can you increase the amount of entanglement between the quantum systems by these type of operations. In any case, there too, the analogy between thermodynamics and entanglement is only limited. And therefore, I think the case of black hole thermodynamics is impressive because there seems to be an explicit analogy, not just for the second law of thermodynamics, but for all of the four laws of thermodynamics. At least this is how it is proposed by Bob Wald and Erik Kuryal. Now, there is a lot to say about each of these different laws and their formulation in terms of thermodynamics and in the black hole theory. But at least you seem to be able to read out that temperature is analogous to surface gravity, that entropy is proportional to the area of the black hole, and so on. As I said, there is a lot to be said about each of these four laws, and if you read, for example, Erik Kuryal's paper, there are about 10 different footnotes distributed to these formulations, and there's a lot of fine print to work through. I'm not going to do all of that, but I do want to suggest that the thermodynamical side of this analogy is, in my view, a little bit misrepresented. And so I want to amend these statements a little bit. And here is what I have in mind. The Zeroth Law of Thermodynamics is not just a statement about temperature being constant in a given body, it's a statement about the relation of thermal equilibrium between two systems. And the orthodox historical formulation of the Zeroth Law is that that relation of equilibrium is transitive. Secondly, most importantly, the second law of thermodynamics does not just say that entropy can only increase in isolated systems. It says that it will increase in any adiabatic process, which is much more general than just a process that happens in an isolated system. And for example, what I have in mind here is a sort of archetypal adiabatic process. You have a fluid in a box, it's surrounded by insulating walls, so there's no heat exchange with the environment. But you can do work on the system, for example, by the paddle wheel experiment that was originally performed by Joule. And in this way, you can actually heat up the system by the stirring device that's inside. So this is a system which is adiabatically isolated from its environment, but it's not isolated. You interact with it. And the second law of thermodynamics says that even in this case, if that system settles down to a new equilibrium state, its entropy will be higher than it was in the initial state. So this is why the second law of thermodynamics does not just apply to isolated systems. applies to any adiabatic process. Of course, if a system is isolated, then whatever it goes through is adiabatic as well, but that's just a special case. In contrast, if there are non-adiabatic processes in which you do exchange heat with your system, then its entropy can increase. So, I would like to amend the thermodynamical formulation of these laws, and to put it slightly differently, I think that in the presentation of this thermodynamics black holes analogy, it appears to me that the formulation of particularly the zeroth and the second law had already been heavily edited to make the analogy look a little bit greater than, or at least to hide notions that will become problematic for the analogy. So let me say a little bit more about what type of theory thermodynamics, orthodox thermodynamics is. And I will have in mind here the tradition of authors who looked particularly at the foundations of this theory, authors like Karen Theodori, particularly also Tatjana Ehrenfest, who wrote several works on this subject, Hans Buchdahl, and one of the most recent is Lieb and Ingverson's axiomatic approach to thermodynamics. So what is characteristic of this approach to theory is, first of all, that thermodynamics is a theory that takes a sort of black box approach to the systems it studies. That is to say, it doesn't really worry about what the constitution of that system is, what it's made of, what's going on a microscopic level. It only describes such systems by their macroscopic properties and quantities. And of course, originally the motivation for that approach was that in the 19th century there were many people who doubted the existence of atoms and who wanted to avoid even mentioning them. Today, of course, we don't have that fear anymore. But the particular approach that thermodynamics takes is still worthwhile, even though you leave out the microscopic constitution. It's worthwhile precisely because if you don't worry about that constitution and you do not make any assumptions about it, the theory will survive any revolutionary changes you might have in our conception of the microscopic world. And so, even though classical mechanics has been replaced by relativistic mechanics and by quantum theory, thermodynamics has not been endangered by these different views about what the microscopic world looks like. And it is still applied in exactly the same form as a microscopic description, even of statistical mechanical systems, about quantum systems, and who knows, even about black holes. So we don't talk a lot about what goes on the microscopic level in the system, but what thermodynamics does look at are the several kinds of processes that you might take systems through on the microscopic level. And there are several kinds of these processes. First of all, there's the notion of equilibration, that the thermodynamical system, if you leave it alone, isolate it from its environment, if you wait long enough, the assumption is that that system will approach an equilibrium state in which none of its microscopic properties changes anymore. Associated with that is the notion of thermal equilibrium, which now is not a property of a single system, but a relation between several of these systems. And of course, the distinction between work and heat, or related to that, the distinction between adiabatic processes, which in classical definition is that a process is adiabatic if it's any type of interaction at all except heat exchange. There's no heat exchange in an adiabatic process. And the converse notion is that of a thermal process, thermal coupling, in which you allow only the exchange of heat with the system. Now, what I particularly want to argue is that when it comes to black hole thermodynamics, it is not just enough to show that there are 4 equations that formulate particular laws of thermodynamics and that look a lot alike. What I want to argue is that you can only have a meaningful analogy of thermodynamics if you can find similar distinctions, so similar processes for black holes. And so let me first go in a little bit further into the distinction between heat and work, or adiabatic processes in the life. So in all approaches to thermodynamics I know of, it is crucial that there are at least 2 different ways in which you can change the state of a system, namely by doing work or by doing heat. And it's not necessarily the case that these 2 cases are mutually exclusive. It's not necessarily the case that they are exhaustive. There might be other ways to change to a system. But at the very least, you have to be these 2 distinct notions. And it's not the case that thermodynamics tells you how to make that distinction, but rather it presupposes that there is a way to make such a distinction. And as I said, an adiabatic process is defined as any process in which you change the state of the system by exchanging in whatever way, or by whatever means you can think of, except that you're not allowed to exchange heat with the system. So that's why this was an adiabatic process. And this is, again, a repetition. A thermal contact is something in which you allow no interaction to happen except the exchange of heat. And this is what I try to illustrate over here. If this is a wall that will transmit heat, it's a diathermal wall, and I have 2 systems in separate regions of this type of contact, then they are in thermal contact. Now, there are 2 different approaches in the literature that I mentioned. There are some who take the distinction between heat and work as primitive and define adiabatic and thermal coupling in this way in terms of heat and work. There are other approaches that take the reverse route and start with taking adiabatic process as a primitive notion and then try to define heat and work in terms of them. To me, that doesn't really matter which of those 2 approaches you take. It's like 2 different sides of the same coin. But you have to have some type of distinction in place here before you can even develop thermodynamics. When it comes to equilibration, there's actually also another assumption that, again, is made in all the texts that I know of in thermodynamics, and which I think history has simply, in historical developments, it simply has been forgotten to recognize as that is also a very basic assumption in thermodynamics, and that actually deserves to be listed as one of its laws. And that is the assumption I mentioned before, that every thermal system, at least in a finite volume, will eventually reach an equilibrium state. And since already the Zeroth Law has already been taken up, together with Harvey Brown, I propose that this should be called the minus first law. Actually, in my teaching notes, I propose to call it the minus infinity law, because there are quite a few other assumptions that ought to be recognized as thermodynamical laws. Yeah.
But this assumption may not be valid if you have gravity, which is well recognized in astronomy. There is a negative heat capacity in such systems once you introduce gravity.
Sorry, I forgot to mention if that system is isolated.
Okay.
Yeah. But negative heat capacities is not a problem for this.
Because what happens under gravity is systems tend to collapse and release even more energy as they collapse. So they don't cool, they actually heat up.
You don't have to cool, because cooling is something that presupposes an interaction with an environment. These are isolated systems, so their energy stays the same.
Right, but gravity allows you to get more and more energy as the system collapses.
But they're not in equilibrium if they have negative spin.
That's what I'm saying, so there will never be a thermodynamic until you make that.
Well, okay, then, it has been a well-known problem whether thermodynamics will hold in gravitational fields and hydraulic and so on. But this is an assumption that is actually made in all of the ordinary textbooks of thermodynamics. So, in any case, once you have two systems in equilibrium...
But I guess it's an assumption which is not true here, which we know is not true, right? We know in classical black holes that the equilibrium state would be the gas of, if you're doing an ensemble with all things of the same energy, if you make it isolated by putting it in a big box, the equilibrium state will be just, and you're fixing energy, the equilibrium state would just be a box full of free photons and gravitons, and it will never reach that if it's classical.
Why would it evolve into a gas of free photons if it's classical?
It won't.
It won't. No.
So the assumption that every thermal system in a finite volume eventually reaches an equilibrium state. I see. Oh, you're going to say it's an equilibrium state, but it doesn't maximize the entropy.
No.
Equilibrium states don't have to maximize the entropy, you're saying.
They don't have to, because in orthodox thermodynamics, entropy is actually only defined for equilibrium states.
But we on a slightly different note though, we do know of some thermodynamic systems, special ones, special mini-body systems, that in fact do not equilibrate. They never thermalize. There are certain special mini-body systems in holography. You can choose, tuned initial conditions where
integrable systems.
What's that?
Integrable systems.
I don't know if they're integrable or not, but there are systems where you could start off with some initial conditions and some perturbations of those initial conditions, and see that they never thermalize.
They're not ergodic, I guess.
Right.
Basically, they're just going to a limit cycle or something.
So the statement here is that if in ADS is if you choose particular initial conditions, you'll never have gravitational collapse. Okay. If If I'm in globally, yes.
I don't think it's necessary in thermodynamics to assume that when we talk about an equilibrium state, it doesn't necessarily has to be a thermal state.
It doesn't
What
have
is
to
meant, what is
maximize
meant
it.
by an equilibrium state is just to claim that the macroscopic properties of the system are constant.
Yeah, I guess.
And of course there are I mean, you can even take a simple harmonic oscillator as a counterexample.
But that's not a many-body system, though.
No.
It's not a.
But there are of course systems that do not reach an equilibrium state. But in textbooks on thermodynamics, it's usually argued that if you look at gases, fluids, if you put ice cubes in a cup of coffee, you leave them alone for a long enough time, you will get to a state where nothing changes. And that's the equilibrium state. Now, it may not be generally true for all types of systems, but it is a crucial assumption in the theory of thermodynamics. So if you find systems that do not obey this assumption, I would argue that thermodynamics is not applicable to them. So, the notion of thermal equilibrium is, as I said, is a relation between two systems. And the idea is that if you put these two systems, if each of them is in equilibrium, and you put them into thermal contact in this way, and the composite system remains in an equilibrium state, then they're also in thermal equilibrium. And now, the main assumption, due to the formulation of the Zeroth Law by Fowler, is that that relation is a transitive relation. Actually, you need somewhat more, namely that it's an equivalence relation. And then the argument is simple, because if this is an equivalence relation, then you can group systems and states in equivalence classes. Those equivalence classes can be labeled, and that label is temperature by definition. So if two systems have the same temperature, then they will also be in thermal equilibrium. And you don't actually have to put them into thermal context to check that. Of course, there's a lot more to be assumed here before we can also claim that temperatures are labeled by real numbers, but I will not go into that issue. So, that is the second challenge that I wanted to propose. What does it mean for two black holes to be in thermal equilibrium? Or what would it be for a black hole and an ordinary thermal system to be in thermal equilibrium? Yes.
You are willing to permit Hawking radiation, right?
I am willing to permit.
I think once you allow that,
yeah,
I think you can cook up situations where you can have these concepts satisfied. Maybe not in the most general sense, but I think a black hole in a reasonably compact box does come into equilibrium with its surroundings, and I think it should be possible to set up two black holes in a box which will come into equilibrium with each other.
That's, yeah.
No,
That be enough?
no, they'll always combine.
They have different temperatures.
In gravity, they're going to
No, no.
just gonna fall.
No, I'm going to hold them there. True, gravity brings them together. This is what Avi is saying. Gravity is a different story. I'm just looking at the thermodynamics.
It's always more entropy if you join them.
Yeah, if you allow them to join, that's a different story. Yes.
How are you going to hold a black hole?
But once you say that you cannot have two black holes, it'll always be one, then none of this makes sense. Okay. I'm trying to invent a problem where I keep two black holes apart.
That's saying there's two boxes.
Yeah, there. Two boxes.
I see. Okay.
Yeah, I'm thinking of exactly the bottom picture there.
I see.
Or maybe the second, the upper one,
yeah.
where you allow thermal
Yeah.
contact, but you don't let the guys merge.
That's right.
Yeah, I think one can come up with toy models
exactly.
which will probably satisfy challenge too.
That's good. Yeah. And as I said, I'm not trying to argue that it cannot be done. I don't try to argue that it can be done. I just think that in order to judge whether this analogy makes sense or whether it's just merely an analogy or partial analogy, you have to ask yourself questions like this. And if you come up with a reasonable proposal, then that's
Okay,
right.
good, okay, we'll work on that.
Yeah.
I think the box has to be small, that's the requirement.
Okay. Now, I also, in the last minutes I will take, also wanted to point out to another problem that you actually also have in orthodox thermodynamics. And that is that everything you can do for thermal couplings, like this one, thermal contacts, you can also do for an analogous type of putting systems into contact, and that is the work coupling. So this is only permits heat exchange, but nothing else. This type of coupling, which is movable, will allow only work exchange between the two systems, but no heat exchange. That's another way in which you can put two systems into interaction with each other. And obviously, in this case too, there are cases where if each system separately is in equilibrium, the equilibrium can be maintained. And that also leads to an equivalence classes, and you can introduce a parameter to characterize those equilibria, and that parameter is pressure. And indeed, you can find a fully worked out symmetry within thermodynamics between, if you replace all the notions in the upper line by corresponding notions in the lower line, then you can generally transform valid statements about one subject into valid statements about the other subject. And so this also leads to actually some kind of puzzle, because we do have a claim in thermodynamics that entropy in adiabatic processes only goes up. And so you might argue similarly that if you have a system in which you do not allow it to exchange any work with its surroundings, then you can never decrease its volume. And that is certainly true if you've got a whole lot of systems, a complex of systems, each one connected by these movable pistons. If you're not allowed to exchange work with its environment, then you cannot possibly decrease its volume. So this would be another analogy to the second law. And this also shows that there are even symmetries within thermodynamics that can lead you to different interpretations of the same theme. And the next question is then, why don't we actually take that claim to be a serious law of thermodynamics? The answer to that, at least as I found in my Tatjana Ehrenfest, is that there's actually another law that is needed in thermodynamics. And that is that although thermal contact is essentially unique, there's only one way in which you can put systems into thermal contact. This work coupling is not, and you can have sort of hydraulic couplings. So, for example, if I have this type of coupling, then in this case the condition of mechanical equilibrium is no longer that the pressures are equal, because it's actually the force equilibrium, and since the areas are different on both sides. And in this case, you can decrease the volume of your total system. And in this case, it's also possible to do work by a system with low pressure on a system with high pressure, whereas it never seems to be possible to let heat flow from a system with low temperature to a system with higher temperature. So there is one more aspect to take into account here, and that is that thermal contact is sort of unique, whereas other types of contact depend on the type of attraction you use to couple systems. And one way of putting this additional law of thermodynamics is to claim that there are no thermal levers in contrast to mechanical levers. So I think that this is also something that should be taken into account if you want to find some notion that characterizes the analogy of thermal equilibrium in black hole theory. You will have to be able to specify what makes thermal couplings unique in contrast to other couplings.
It's the lack of Maxwell's demon.
Yes. So that is what I wanted to argue, and once again, I'm not saying that it cannot be done, I'm not saying that it can be done, I'm just saying that that is something that the attention in the debate, I think, should focus upon. And yes, of course, Hawking radiation is some possible mechanisms by which black holes can interact with their environment. Eric Curiel wants to claim that this, of course, that's true, but that the analogy even extends in the classical level where you have no Hawking radiation. He argues that the necessary interaction might be the role of the necessary interaction might be played by gravitational radiation, although it's not clear to me that that will always work, because I think there might be there will be ways in which you can interact with the black hole that do not produce gravitational radiation, because it seems to depend on the Archetypal. But there has to be a mechanism for how systems can equilibrate, and again, as I also said, we also need to be able to distinguish, in some principle sense, an adiabatic process from non-adiabatic process. And that is something that I have never seen discussed, and I think this is partly due to this very careful editing of the original thermodynamic laws, which makes it look like thermodynamics never even mentioned the notion of adiabatic. But that, I think, is a serious misleading way of presenting the subject. Thank you very much.
Time for a quick question.
So would you think it would make sense to a third answer to that question? Might be that thermodynamics is imperfectly derived from statistical mechanics of microscopic constituents, and that if we can, and there are puzzles about that, as you've discussed, that's not a complete story, but it's certainly a compelling story, at least part of which is true, and that identifying all the microstates of the black hole would in some precise sense, would reduce this problem of deriving the analogy to understanding the transition from statistical mechanics to thermodynamics for black holes, which would likely be subject to the same kind of caveats and uncertainties that the usual derivation of thermodynamics from statistical mechanics would be. In other words, one could imagine putting the analogy at the beginning rather than at the end.
Well, if I understand the approach you're sketching here, my sense of it is that I would consider that to be a case of a analogy between, well, the statistical theory of black holes and the statistical mechanics.
Well, it wouldn't be it would be more than an analogy. It would be a system with many degrees of freedom,
yeah,
to which one could apply statistical methods. Then there's always problems in applying those statistical methods in any real context. And black hole would presumably be no exception. It would always have these problems.
Gravitational degrees of freedom have always been a big problem in statistical mechanics, precisely because of the negative heat capacities and the non-existence of thermodynamical limits and so on. But to repeat, you can very well take a point of view that thermodynamics is an imperfect theory and that it's not really valid in the real world. But
Well, I wouldn't say that. I wasn't suggesting that. I
you
mean,
would.
I'm agreeing with what that quote of Einstein we were discussing the other night, that in 200 years thermodynamics will be the only thing that will survive.
Statistical mechanics.
No,
Does he say statistical
I
mechanics?
think so,
No.
yeah. I
Einstein
think the methods
is-
of statistical mechanics.
But if statistical mechanics survives, so will thermodynamics, right?
Einstein said,
Yeah, right.
Einstein said in his autobiographical notes that thermodynamics is the only theory of which he was convinced that it will never be
Oh,
overthrown.
Yeah,
And he says thermodynamics.
It is
He says
thermodynamics.
thermodynamics,
Okay,
and
I
he
thought
says-
it was statistical
And he
mechanics.
says that he brings this to the attention with the special attention for those who are skeptics.
That's why he modeled special relativity on thermodynamics.
Yeah.
His first two assumptions of the laws being independent of frame of reference and the speed of light being absolute were supposed to be the analogy of the starting points of the first and second laws of thermodynamics.
But Einstein was wrong on some occasions.
The first
so
law being
the
the
fact that
entropy
he
is
said it
zero?
doesn't mean
Wait, what's the first?
Conservation of energy.
There was no zero.
okay.
There was no Zeroth law at that point. So, but he thought of them as analogous to the laws of thermodynamics, in the sense that we don't have a precise theory about how light is how it interacts with matter. But we are not concerned with that question. We only assume that the velocity of light is independent of the speed of the source. Whatever is the mechanism is that by which light is emitted.
Yeah.
So you just take a sort of black box approach. You don't worry about what goes on at the most fundamental level, and you simply postulate that there is this empirical regularity.
Yeah.
So that's what he characterized later as his theory of principle approach.
But I think it's fair to say in practice that many physicists are very concerned with your top question.
This
And-
one?
Yeah.
Yeah.
But they would not recognize either of these two as the method by which we would answer it.
No, well, there might be other methods. Yeah.
Yeah.
But providing a statistical theory, I think, is not necessary for judging whether there's an analogy between thermodynamics and black holes.
Right.
But it could be a way to investigate the problem.
Yeah.
perhaps we can hold off conversation after the colloquium. If we could thank our speaker one more time. One further shorter talk. And it's a delight to introduce Tiffany Nichols to the Black Hole Initiative Colloquium series. Tiffany is a PhD student in the Department of History of Science here at Harvard, and she completed a bachelor's degree and a JD at the University. It's a fearless leader in philosophy, I think. She did a bachelor's degree in electrical engineering and a JD from the University of Virginia, and she works on the history of site selection for large-scale interferometers, particularly in the context of detecting gravitational waves, and today she's going to tell us about geoepistemological site selection for Ligo.
Thank you for having me, and thank you for the introduction. So my talk is set at about 15 minutes, so here we go. Ligo's work can be roughly described as filtering environmental disturbance noise from the very minute signals generated from gravitational waves. So therefore, Ligo's epistemology can be described through its understanding of what type of noise counts and what type of noise does not count. So with respect to the site selection of Ligo, this process focused on finding sites which reduce noise, and the tool of choice to guide the process was the map. Thus, the map served as a mediator between the science of Ligo, and the actual space Ligo would ultimately occupy. So, this talk focuses on the role of the map during Ligo's siting history through analyzing what William Rankin has termed as geoepistemology, which is concerned not only with the knowledge gained through the map, but also one's existence within the space, or how one's existence within the space impacts one's understanding of the space. So Rankin explains the power of maps lies in their ability to act as a stand-in for the original landscape, resulting in a state where the map and the territory become one. So thus, the goggles of geoepistemology come in many styles, but they can never be removed. So in focusing on the roles of maps, my research reveals variations in geoepistemology resulting from the activities which increase the power of the maps and activities which decrease the power of the maps. These activities sought to gain a Borges-style understanding of the represented landscapes, where Borges imagined a map so accurate it was the size of the city it depicted. So this talk will be organized in the following parts. So first we'll explore the geoepistemological understanding resulting from actions which increase and decrease the power of the maps through reviewing the utilization of sources and activities outside of the map. Then we will closely analyze the geoepistemological understanding of the Livingston site, which experienced unexpected seismic noise, whose source was a mystery for quite some time. So focusing first on the activities which increase the power of the map, scales and credit legends of the maps are often removed. For example, here's a stack of credit legends, which you can effectively call map metadata, removed from several 7.5 minute topographic series USGS maps, which were used in the site selection process for Ligo. So when asked why these credit legends were removed, Ray Weiss indicated that the maps were too large to fit on the copier machine. So taking a closer look at these removed credit legends, we can see the information concerning the space, or the information that was lost concerning the space. This information included scale, distance, features and characteristics of the land, how current the map's features are, and the methods used for collecting the map data. So in addition, the coloration was often removed. This was likely due to save costs. So this coloration was removed from some of the maps that were reproduced in reports and documents during the decision process, often resulting in misjudgments of population size and growth. Edwards Air Force Base was proposed in the Blue Book as a potential site, so we'll start by looking at the map that as it appeared in the Blue Book. We can see the color, the credit legends, and portions of the maps were removed. So exploring what understanding was lost further, this is a portion that was circled above of the Andrews Air Force Base. A version of the 1958 map, which was the one that was used in the Blue Book. Remember that site selection started in 1983. That's on the right, but on the left is the next version of the map in 1966, indicating changes in populations and boundaries near the candidate site. So this was lost by removing the coloration. And to gain a sense of what additional information was lost, I have arranged a portion of the map using the Blue Book with the entire surrounding area. And interviewing Ligo physicists involved in the site selection process, including Kip Thorne and Stan Whitcomb, and reviewing archival material, Andrews Air Force Base was initially one of their preferred sites due to its placement in the Mojave Desert.
Excellent.
Yeah, and so Edwards is here, and you can see this whole white space is the Mojave Desert. So it's got to be pretty quiet. So also, it was close to Caltech, which is at the bottom, and JPL had established presence on the base, and they were consultants for Ligo at the time. So the tricky thing about maps and military bases that I remember growing up in a military family is that not every building, street, or road found on the base is depicted in maps of the base, and further, some bases appear quite quiet from the outside, but once you're inside, they're effectively mini cities. So we can see that happening here. The map depicts a more quiet space. So as Ligo focused on Edwards, it became apparent that there was a significant level of military activity on the site, and the space was not accessible without permission from the Air Force. Further, Edwards contains varying spaces of accessibility within its borders, so therefore, in order to navigate within that space, one would have to require varying levels of security clearances, which impacts the international nature of Ligo and the LSC collaboration. So as we can see further, there's also an Air Force Flight Test Center, which is part of Edwards Air Force Base, and then the San Andreas Fault runs between Los Angeles and the Mojave Desert. So these noise sources were literally falling off the map that we saw in the Blue Book, which could have contributed to the push for the interest in this site. So now shifting to actions which decrease the power of the map, coloration comes in again. So generally in maps, coloration has specific meanings. So we generally equate green with wilderness and quiet. So such arguably misleading features were at play in the candidate site of Columbia, Maine, which was initially identified by the Maine State geologist as quiet. However, Ray Weiss was able to adjust his geoepistemological goggles when he visited the site. During these visits, he learned that the green spaces were not as serene as the map depicted. Instead, the land was used by blueberry farmers and their workers who tended to and harvested the land with heavy machinery. And Weiss was able to further adjust his geoepistemological goggles to working with an attorney to determine the ownership of the land, which turned out to be owned by at least 10 farming entities. So imagine multiplying this machinery that you see here for blueberry farming or harvesting and multiply by 10, and you can think about the noise generated from that. So the map also shows another source of inherent power and the discretions of cartographers. So USGS specifically states, many persons who use maps are not concerned with the exact ground elevations, but are more interested in the general appearance of the shape of the land. So when we turn back to the Columbia Maine site, its depiction of elevation land was within the accuracy of 20 feet, which was not sufficient because the elevation changed every few feet in this area, and the interferometer arms, as we all know, must be constructed on an absolutely flat and straight surface. So exact knowledge of the fluctuations of the land is very important. And to exacerbate this even more, this is part of the credit legend that was removed to help you interpret these elevation lines. If you were to actually draw the elevation changes in this space, this would be a sea of this burnt sienna. The whole map would be covered because to get the level of detail, we would not be able to actually discern the elevation because the map would change from green to a sea of elevation lines. So also, it was determined over 60 years after the creation of the underlying map data for this map that was used in the Ligo process that the data about elevation was incorrect due to faulty surveys conducted in 1927, which were carried forward until the maps were drawn after 1987. Weiss realized that the maps were inaccurate due to his site visits with the state geologist, and he was able to adjust his geoepistemological goggles by commissioning his own land and aerial surveys, which provided the level of accuracy needed to build and construct the interferometer. So, the Livingston site faced similar coloration issues as shown in the Livingston area map here. The team believed that the site was ideal due to the placement in the middle of a pine tree forest, and was thought to be mostly quiet because it was only harvestable every 20 to 30 years. This perception was supported by the physicist who identified the site, and also conducted his own seismic surveys of the site. So the results of this survey confirmed the green quiet spaces of the map and allowed the claim to be made that the site was 10 to 30 hertz quieter than all the other candidate sites. So on the right here, we have the seismic survey, or the map, and the location of where the seismometers were placed in the seismic survey done on the Livingston site and included in the Livingston proposal. So although the seismic survey was an attempt to decrease the power of the map through trying to better understand the space, once again, the scale, credit legends, and portions of the map were removed, changing the geoepistemological understanding of the space and increasing the power once again. The map on the right shows where the interferometer is now situated. The blue dots show where the seismometers were placed. So to drive between the interferometer arm and the space would probably take about 5 minutes, going about 50 miles an hour, so they're quite far away. So although the seismic report was not used as a comparative factor, the claim that the space was 10 to 30 hertz quieter was used. So this qualification that Livingston was quieter than the other sites, paired with the green colorization of the Livingston map, likely defined the geoepistemological understanding of the space, as the site was consistently described in the report by the committee who suggested sites to the MSF as having a low duty cycle, or the forestry activity had a low duty cycle, and it was estimated that this activity would only occupy 2% of the time that Ligo operated. So, however, once the site was up and running, the interferometers cannot be placed in a locked state during the desired period of time during the day due to seismic noise. And this particular vibration was of concern because it was within the frequency range that would mask potential gravitational wave signals. So this yellow box is trying to say that as this tree activity is going on and causing seismic vibrations, any signal in that area might be masked, the gravitational wave signals coming through. So it was Weiss who realized that the culprit was the tree harvesting right in their own front yard. So here's the interferometer arm in Livingston, and the trees are surrounding the entire site. So specifically, Weiss adjusted his geoepistemological goggles by identifying the culprit vibration while in the control room at the Livingston site and running outside when he noticed that tree harvesting activity. He explained that this was the most undesirable noise because the falling trees create Rayleigh waves. So here's some excerpts from the Ligo weekly log when Weiss discovered this problem. Specifically, he states that the logging activity in its current state would have to be more than 225 kilometers away from the site, but as you saw in the photo, it's merely several feet away from the site. Next, Weiss ponders about acquiring a 10-kilometer radius around Ligo. However, this would cost $230 million, but as we know, Ligo is already quite expensive at this point. So, therefore, the only solution, he says, is the engineered solution. So, although the maps indicated a forested space, was also effectively depicted a pine tree harvesting forest, it did not indicate the seismic noise generated from the harvesting activity. So therefore the space, as represented on the maps, became the understanding space of the Livingston site. So in conclusion, Ligo researchers engaged in activities to address some of the geoepistemological goggles of the maps, however, inherent blind spots remained. As we all know, these issues have been resolved because there have been 6 detections thus far, made possible through the engineered solutions to effectively filter out noise and keep the instrument still. But during the selection of new sites for future interferometers, one must consider the power of the map and the extent of our ability to compensate for unknowns not expressed in the map, to avoid unexpected costs due to our blind spots in our geoepistemological understanding of land and space. So, thank you.
So now that the Nobel Prize was awarded to this, is it possible to convince the people not to harvest nearby?
No, they actually, all the observation runs, if you notice the dates, are not really in a set pattern. It's often because they have to wait for these trees to be cut down. So there's still some
But do they realize the impact that they had on the science?
Well, Livingston is very excited about Ligo, but you can say it's an area. So these pine trees are used for paper towels and toilet paper, and so that's very important to them.
Yeah,
So,
but they can cut trees somewhere else,
yeah, arguably, but this is a very special environment that allows for these pine trees to go pretty quickly. So there's competing.
But what's more important, finding black holes or this?
This
Or
stuff-
toilet paper?
This stuff literally grows on trees, right? So.
Yeah.
It's just Andy in the room.
I'm curious, there are also, of course, conservation organizations that are interested in preserving big swatches of old-growth forest, didn't they? There was never any discussion with, they try to raise money.
Oh, in Maine?
Yeah.
Yeah, so the main site, this particular site, the biggest issue was blueberries, but also there was thought to be artifacts from indigenous people who
But
the site.
they're conservationists who want to preserve the forests and not see them logged.
Oh, well, this is already farmland, so the main site is already dedicated to blueberries.
To blueberries.
Yeah,
I
so
thought
they
you
were.
said forest and logging.
Oh, in Louisiana, it's the pine tree forest.
In Louisiana. it's
Yeah.
fine.
Mm-hmm.
So, Tiffany, I thought in the beginning you said
Yeah.
that this Louisiana site, the logging was supposed to happen once in 30 years.
Yeah, that was the original thought.
Yeah, how did 30 years become daily?
Oh, it's always been pretty regular. So it's every couple months, and then they do various activities. So the site itself is actually like a 30-mile radius, and so they're doing different things in different spots.
They get through the whole thing every
Okay.
Yeah.
So each spot once in 30 years, but there are enough spots to keep the place active.
It also went out, I think it went out a lot farther than they thought.
Yeah.
I mean, that what Weiss discovered, what Ray discovered was that even 225 kilometers away, it was a problem.
Yeah, exactly.
Just to continue Avi's original question, what do people think about Ligo? I mean, you've spent a lot of time in these sites,
Yeah.
like Louisiana. How do people see the experiment from the forest, the foresters and the people that live within a range of the Ligo?
Okay, so almost everyone loves the project. So there's an awesome science center there. It's very connected with the education system. There are internships between colleges and universities. However, the economic development sector is not too fond of the project because Ligo created about 40 jobs, and they're used to bringing in industries that create 200 or more positions. So this is a very manufacturing-heavy area of the country, and Ligo, by the individuals who want to develop that aspect, wasn't seen as the best site to have there. So
one way to solve the problem is to bring, for example, an Amazon center there so that they won't cut the trees and they will work on something else.
yes.
Buy a couple hundred square miles of rainforest and preserve it and have a barometer there.
Yeah. Well, thank you.
Okay,
Thank
big
you,
round of
Tiffany.
applause.